All right, folks, back for day two of our intro to linear and nonlinear functions. Warm up for today is to determine whether each example is linear or nonlinear. So what I want you to do right now is take a look at these and make your best guess. Some of them are pretty easy. We're just going to go through and just basically say this is a linear function or nonlinear function. So pause the video, have a response for A, B, C, D, E, and F, please. Now we're going to start with A. Remember, the definition of linear is an equation or a function that represents consistent rate of change, or represents a consistent rate of change. I look at A and I see the x values going up by 1 each time. We go from -2 to 1, or -1, that's an increase of 1. -1 to 0, increase of 1. Another increase of 1. So they're all going up by 1 with the x's. We just need to see if there's consistent change in y. So with y, you go from -7 to -4, increase of 3. Here's another increase of 3, another increase of 3, and another increase of 3. This is what's known as the rate of change, okay? 3 per 1. So that would be linear. That's a linear function. We'll label that up at the top, linear. Okay? Letter B. Graphs are a little bit easier. If it's a straight line, you tell that it's linear, and in this case, for sure it is. So we're going to say that that's a linear function as well. Letter C, graph. Now an equation. We talked about linear functions having that form mx plus b. One of the biggest rules when it comes to linear functions is that the x is raised to the first power, or that there is no exponent shown there. Okay, the 1 is kind of implied. With letter C, y equals x to the 4th power. That 4th power makes this a nonlinear function. Okay? Nonlinear, just because of the 4th power, basically. Going to show change that is consistent, but not in a linear way. Scroll down to D. Now, this is a little tricky. People get this one confused. This is actually an absolute value function. The line goes down, then straight up again. All right, so even though it kind of looks like two lines, this is considered nonlinear as well. All right, just because of that V that it shows. Letter E, 2x plus 1, that's for sure in mx plus b format. With the m rate of change being 2 and the b being 1. So yep, this one's linear. And then letter F, as I look at that, my independent variables are going up by 1. This is an increase of 1, this is an increase of 1, increase of 1. My dependent variables, however, going up by 6, and then going up by 12, and then going up by 24. So it has a pattern to it, just not a linear pattern. This is a nonlinear function. All right, so today what we're going to do is continue to explore the difference between these two things, and maybe provide a little bit more context and clarity to the concept itself. All right, now we're going to start with the pizza question. Everyone likes pizza. All right, Pizza Barn, in my opinion, offers the best pizza in the area. Yeah, I said it. Okay, they offer a 1-topping pizza in 3 different sizes, and those sizes are shown below. My question is, which option offers the most bang for your buck? Now, I wrote this question last year. They may have changed the actual costs. What I want you guys to do is take a moment here to decide which option allows you the most pizza for your dollar. Because the answer is actually a little bit hidden. So you got a 6-inch diameter pizza for $5, a 10-inch diameter pizza for $10, and a 14-inch diameter pizza for $14. So take a moment to write down your response, or think about your response right now. Which one gets you the most bang for your buck? Now, the most popular option is the 6-inch pizza. Okay, most popular response, I should say, is the 6-inch pizza because when you think about it, you get 6 inches of diameter for $5. Okay, that's a ratio of 6 inches of pizza per $5. Whereas with the $10 and the $14 pizza, you're getting basically an inch per dollar. 10 inches for $10, 14 inches for $14. So the rate of change when we're talking about the diameter of the pizza in this situation is about 1.2 inches per dollar. Over here, it's about 1 inch per dollar. Same with the 14-inch pizza, 1 inch per dollar. All right, so you can see here, in terms of the diameter of the pizza, you definitely pay for or get more for what you pay with the 6-inch pizza. However, when you think about a circle, all right, circles are, or when we're talking about bang for buck, we want the most area out of the pizza itself. So what we're going to do first initially is to just examine the area model and take a look at which one actually is the best deal, because this is important math to be able to figure out. Right? When comparing pizzas, we should use the area model instead of simply calculating the diameter of the pizza. Now, area is a result of taking pi times the radius squared, with the radius being exactly half of the diameter, if you guys remember these formulas from last year. All right, so let's take a look. Radius compared to the area. Now, we had a 6-inch pizza, which would have a radius of 3. We had a 10-inch pizza, which would have a radius of 5, and we had a 14-inch pizza, which would have a radius of 7. So when we do the math on this, right, the area of a 3-inch radius pizza would be pi times 3 to the second power. Okay, area of a 5-inch radius pizza would be pi times 5 to the second power. 7-inch pizza would be pi times 7 raised to the second power. So this function is technically nonlinear. And when we sit down and do the math with what pi times, what would that be, 9, or 9 times pi? I'm just going to use 3.14 as pi, by the way. 3.14 times 9 gets me an area of 28.26. 28.26 is the area of that pizza. With 5 being the diameter, I take 3.14 times 5 to the second, which is 25. That gets me 78.5. And with the final one, pi times 7 to the second, that's 49 times 3.14. That gets me 153 square units, or square inches in this case. I'll round this to 9.9. Okay, so you guys can see that the numbers are increasing by an inconsistent amount, therefore this is a linear or a nonlinear function. Now let's chart this out to even better represent it. If we've got area over here, and we've got the radius down here, all right, I'm going to show these different amounts with the radius of 3. I don't know, let's go up by 25s. So let's say this is 50, 75, 100, 125, 150, 175, 200. Okay. With a radius of 3, you guys can see that our area is not super large, it'd be somewhere right in here. When we take the radius of 5, though, it jumps up to 78.5. Should be somewhere about right there. And then the radius of 7 would get you all the way up to 153. So we're somewhere right here. Area or radius of 0 would be obviously an area of 0. And this function, when you graph it out, actually is one of those nonlinear change models, right? A big part of that is the fact that that independent variable is being squared. Okay, the radius is being squared. Now, when we take this back to the original question and examine the, per dollar part of it, remember those numbers. This is 28.6 square inches per $5. right? This one is 78 point, gosh, what was it, 5? 78.5 per $10. Okay, and the last one was 153, I think it was, per $14. When you do the math on all of that, the best possible option is actually the 14-inch pizza, okay? In terms of per dollar. Large units, best per 1 unit. Okay. So again, there's a lot of different examples of linear and nonlinear functions. We take pizza again. Notice you got a theme today. Cheese costs about 80 cents per 4 ounces. Show this on a graph and write an equation that relates ounces to cheese. So if we've got the ounces over here as our independent variable, and then the cost as our dependent variable, we've already got 4 per 80, which means that we've got approximately 20 cents per 1 ounce. 1 ounce is going to be 20 cents. Okay. 2 ounces is going to be 40 cents. 3 ounces is going to be 60 cents. Well, now we've got linear change because those amounts are increasing and decreasing at consistent rates. All right. For to graph out money spent on cheese versus the ounces of cheese, with 1, let's just go by the same units, 20 cents, 40 cents, 60 cents, and 80 cents. You've got 1 being 20 cents, 2 being 40 cents, 3 being 60 cents, 4 being 80 cents, and that values, or those values will increase in a consistent manner, okay, a linear manner. So again, the biggest difference. Okay. A lot of differences out there between these two different types of functions. The biggest thing is understanding why, all right? This is a different type of a graph. It's a bar graph. You can see that this is nonlinear change. This is actually, from the first couple weeks of COVID, this is the positivity rates in some certain area. I don't remember exactly what it was. But you can see that they're not increasing consistently. You can have some upward increases, some downward, some upward, some downward, some upward, and then a big spikes, right? But the fact that that change is not consistent makes this nonlinear. Right? So nonlinear function is a function whose graph is not part of a line. We've got several different examples of linear functions. Nonlinear functions might look something like these 3 at the bottom. Okay, this is 3 different types. This is called a parabolic curve. This is an x cubed function, and then a absolute value function. But nonlinear essentially just means it's not part of a straight line. Another way that we can tell is by just kind of looking at what power the x is. We said that this value, or this equation, 3x plus 2, would be linear because it's in that mx plus b format. If you look here, x has no power. Okay, and if x has no power, it's linear. If x does have a power, like x squared is a parabolic curve. Okay, this is going to have a U shape when graphed, nonlinear. Right? X cubed functions. This is the cubic function. Generally has kind of an S shape to it when you actually graph it out. That was horrible. You guys get the idea. Again, nonlinear function, a lot of it comes down to just that x cubed. All right. 3 to the x, this is called an exponential. We'll learn more about these later, but you just kind of have to generally be able to look and know what type it might be. The x is the exponent. In terms of general shape for this one, it's going to have an exponential growth look to it. All right. Y equals absolute value functions will have 2 straight lines going in opposite directions because the absolute value of numbers is telling you basically how far that number is from 0. And a number like -3 has the exact same absolute value as a number like +3. So that's why this would result in a B. All right. Alright, writing equations, we'll come back to this. We talked a little bit about it yesterday, but just coming back to it, just remember these two definitions. M is the rate of change. B is the initial value, or the value of y when x is 0. One way to find the rate of change is to figure out the change in y divided by the change in x. Right? How much does y change in relation to one singular change in x? So when you look at this table, for example, identifying my m value, I'm going to find the change from the number 3 to 5, or 5 subtracted by 3, and divide that by the amount of change from 1 to 2. 2 subtracted by 1. That will tell me exactly what my rate of change is. So 5 minus 3 is 2 over 1, and when reduce, my m value is just going to be 2. And you can kind of see that the numbers are growing by 2 per 1 in x. Now the b value is going to be the value of y when x is 0. There's a couple ways that you can get there. You can literally just trace this back one if you want to, and say if this value was 0, what value of y would result from that? Which I think if you trace 3 back by 2, that value would be 1. Okay, so this equation then is going to be 2 times the x value increased by 1. And that pattern works. 2 times 4 plus 1 gets you 9. 2 times 5, or 2 times 2 plus 1 gets you a 5. We can also find future ones. 2 times 10 is 20, plus 1 gets you 21. So we can extend the pattern a little bit as well. All right, let's find rate of change for this one. Identifying my m value. Again, doesn't matter which ones you pick. I picked the first two on the previous slide. Let's choose this one here. So from 5 to 3, okay, we take 3 minus 5 and divide that by the difference between 2 to 3. Okay, that gets me a change of -2 per 1. So my m in this situation is just that number reduced, -2. So I'll put that in here. The m is -2. The b value is going to be the value of y when x is 0. Well, in this situation, that's given right here. Okay, value of y when x is 0 is the number 9. So boom, y equals -2x plus 9 is my function rule. Try just one more, and then we'll kind of recap the lesson. Ooh, this one's a little trickier. Numbers are in a little bit of a different type of an order. So let's choose again. Doesn't matter which ones we choose if it's linear. From 13 to 28. So that's a difference of, let's see here, 28 minus 13 is a difference of 15. For every 5 to 8, 8 minus 5 is a difference of 3. So when we reduce that number, that's our slope or our m value. 15 divided by 3 is 5. So the numbers we can tell then are increasing 5 per 1x. All right. Now this one requires a little bit of algebra to figure it out. You guys all try this in your head. If you take 5 times any of these x values, what do you have to then add or subtract to get to their y value? So I'm going to take 4. If I took 5 times 4, that gets me 20. To get from the number 20 to 8, I have to subtract 12 to make this work. Let's see if that works for others. 5 times this value of 5, 5 times 5 is 25. If I then subtract 12, that gets me to 13. 5 times 8 is 40. 40 subtracted by 12 gets me 28. So my b value in this situation is -12. All right. Y equals 5x minus 12. So a function rule really just relates the two, relates the x to the y in a really direct way. Now a little lesson recap. Okay, the biggest thing for today was that we understand these differences between linear and nonlinear. Okay, the left side, a graph of a linear function is straight. Okay, you've got something that increases at a consistent rate, something like that. Okay, the table is going to be a constant rate of change, and your equation can always take the form y equals mx plus b. Y equals 2x plus 1. Y equals just x plus 5, right? With the m value in that one being 1. A nonlinear function is a graph that's not straight, okay? Any curve to it, exponential functions, quadratics. The table is going to have inconsistent change to it. In the equation, there are many types, but the biggest thing is they generally contain exponents. All right. That's all for today, folks. Hope the video helped. You guys can get to work.